Morning. My name is I'm Dr. Peter Homel. I'm the Director of Biostatistics for the Department of Pain Medicine and Palliative Care, and most of my efforts are involved in pain medicine, and but also I'm doing some consulting work for the Center for Obesity Research at St. Louis Roosevelt, for the Center for Health and Healing, which is our complementary medicine center, and I'm also doing some work with endocrinology here. So I'm pretty busy, but it means I'm popular. So anyway, this morning we're going to talk about things that are a little bit more general in terms of application to research. So we're going to be talking about tests of mean differences. Contrary to what I originally put in, I decided to put a chi-square in with correlation because it makes a little bit more sense. So this morning we're going to be talking about mean differences, and we're going to be talking a little bit about samples, statistical tests, and p-values as a background. Then we're going to talk about t-tests for two groups that are not correlated with one another, tests for correlated samples, so like usually before and after designs. Then some things like non-repeated and repeated measures in ANOVA. We're going to touch on non-parametric statistics and why they really aren't used anymore. And then we're going to talk a little bit about mixed model regression and generalized linear modeling, which are kind of the waves of the future. So let's talk about medical research. Basically, medical research is interested in patient outcomes. We want to know we're always interested in improving things for our patients. We want to do things better for them. We want to improve their care. And so the whole idea is we want to see what differences what group differences make a difference in terms of their outcome. So we might be interested in a clinical trial where one group of patients gets placebo, another group gets the actual medicine. And we want to see whether or not the actual medicine relieves their pain. Does their pain go down on this usual scale from 0 to 10? So we want to see whether that makes a difference in terms of their outcomes. A lot of my work is involved with looking at caregiver burden. And so one of the things we're interested in is what are the factors that are involved in caregivers feeling more stress, more burden. And so it could be things like age, it could be the fact that it could be a child taking care of a parent that causes more burden. So these are the kinds of things that you want to see whether or not what things make a difference and what things could you possibly do to improve things for the patient in terms of the patient outcome. So we basically want to do statistical analyses to compare differences between groups and decide whether the differences are significant or not. What does that mean? Well, let's talk about samples and populations before we talk about significance and stuff like that. In research, we usually look at samples of patients rather than entire populations. The reason for that is practicality. You can't look at the entire population. Even the U.S. Census has problems looking at the entire population of the United States, so we're certainly not going to look at all patients in the hospital. We don't have enough time, we don't have enough money, and NIH ain't going to give us billions of dollars to do this sort of thing. So we always use samples, and what we try to do is we use the samples to try to generalize to the entire population. So it's the idea that what we find in the samples, the kind of differences we find, the kind of improvements we find in the samples, those are the kinds of improvements that will hold for the general population if we do the same thing for them. So if patients with chronic pain get medication and they get better, so the mean pain goes down, we want to say that the population of all patients who get that same medication will also do better. Okay? Statistical tests, basically, they're mathematical equations. You take numbers, you put them into the equation, you crank out an answer, and you get some result that is either between 0 and infinity. That's basically what a statistical test is. The top usually measures how much difference there is between the groups. And the bottom, the denominator, tells you how much overlap, how much variability there is in the sample. The bottom is the enemy. The bottom basically is what we want to get to be as small as possible, because the bottom is like the fuzz factor, the thing that, the overlap between the groups. It hinders our ability to see that there's a difference between the groups. We'll see how that works out later. Based on the statistical test, we get we can actually calculate a probability for that statistical test. And that probability is called a p-value. And that tells us that if there were no differences between the populations from which our samples came from originally, what the probability of getting that statistical test would be, or getting a statistical test that high. Okay, because basically, if you roll dice, or if you like flip coins, flip coins 10 times, you expect like 5 times heads, 5 times tails, but that's not how it works out. There's randomness, and so no matter the fact that they should be equal, they're not, and from time to time you'll get little differences. And so the fact is that you have to have some way of telling whether or not that coin is unbiased, whether randomness is really operating, or whether the coin is unbiased and randomness is no longer operating, and that you've got something different from what you would expect from just random chance. Probably the best way of illustrating this is with using the example of a randomized clinical trial. So when you randomize in a clinical trial, well, first of all, what you do is you take samples from basically the same patient population. So you've got 2 groups, and since they come from the same population, they should be equal to one another. And then, so if you you randomize, and you've got 2 groups that are from the same population. They've got to be equal to each other. They might be a little bit different from each other in terms of the age and other things, but they shouldn't be significantly different from one another at the very beginning before you do anything to them. Then you give one group an active treatment, the other group the placebo, and if there's no effect of the treatment, you expect that afterwards what you measure is going to be just like random chance. There's just going to be a little bit of difference between the groups. But if the medication is effective, you expect there's going to be a substantial difference between the groups. And so if that big difference is big enough, it kind of tells you they're no longer part of the same population. One group has gotten medication that's been effective, and so they're no longer equivalent to the population where they came from. They're no longer equivalent to the population of the other group, the placebo group. Yeah?
Yeah, I hate to interrupt the flow, but this is an issue that's going to come up from time to time. It's the difference between a p-value, which assesses the probability that a particular difference could arise by chance if the null hypothesis were true, and making a decision about rejecting the null hypothesis.
Yeah.
And I guess I'm a little bit concerned by your last comment, saying that a big enough difference between samples allows you to say that the populations are different, i.e. reject the null hypothesis, when you've just said and pointed out that occasionally you get big differences by chance.
Yeah.
And it's not a small thing, because it relates to the idea of saying there is a true difference because a single sample gets a p-value of less than 0.05.
All right.
It's the difference between alpha and a p-value.
Yeah, that's my next slide.
Yeah, all right. No, I understand, but I just want to just caution that implication doesn't fall out of that bullet point.
Okay. All right. So probability and p-values. So the whole notion of probability is that we've got some number that tells us how possible some statistical test is, and that probability ranges from 0 to no probability to 100% or 1, which is completely probable. And the p-value is the probability of getting a test difference based on the assumption that the samples came from the same population. And I'm also avoiding things like null hypothesis and some other things, because this is really an introductory lecture. If I had more time, if this were an ongoing class, I would get into more of the nomenclature. A large p-value is associated with a small difference between your groups. And it means that it's more likely the samples came from the same population. A small p-value is associated with a larger difference, and it indicates it's less likely that the samples came from the same population. And this is usually what we'd like to get, because it shows that whatever we did in terms of a treatment had some effect. Statistical significance has to do with what we decide is a small enough difference to say, yeah, there's a real difference between these two groups. They no longer come from the same population. And so usually, probably by most statisticians, and it's almost kind of almost religiously observed nowadays, a value of 0.05 is considered the cutoff point, the threshold, so that if you have a p-value that's less than 0.05, then you have what's considered a significant difference between your groups. And so you then conclude that they're not part of the same population. They come from two separate populations. Yeah.
You see the problem here. We spend a lot of time trying to deal with the confusion between the p-value for testing a particular piece of evidence and the alpha level, which is the confidence we would like to take in general that the null hypothesis is true. They're not the same thing, and your slide implies that it is. That you do one single test, and that allows you to assess the universe of information that allows you to say that the likelihood of the null hypothesis is less than 0.05. Alpha is a decision that you make about how comfortable you're going to be with the total amount of evidence. The p-value is something that's calculated with the assumption that the null hypothesis is true. Your second point and your third point are logically inconsistent.
So, Jim, why don't we, since some others of us would like to weigh in on this issue, why don't we let Peter finish and then we can...
Okay.
All right.
Sure. All right. I mean, it's just something that is a lot of problem when we're trying to teach people how to assess evidence.
Okay.
So I'm sorry to, you're right, I'll lay on. I just want to make the point.
All right. Anyway, I have a note here that there's no such thing as a zero probability for anything in life, and so especially when you there are some people who get results from statistical packages that have a p-value that is equal to 0.0000, and they then try to report that as the p-value was 0. Basically, it just means that the p-value is very low, and so that it's less than whatever the number of digits is allowed for by that program. So in that case, the normal practice is to report that p-value is less than 0.001. Okay. Let's talk about t-tests for independent sample means. So basically, we've got a numerator that has the difference. Here we've got two means from two separate groups that we want to compare. So the difference between those two means goes in the numerator. And then in the denominator, we have measures of how much variability there is in each of those samples. And so in that the square root sign, you've got the SD, or the standard deviation of one sample squared, and the standard deviation of the second sample divided by n. And this is the formula that's actually for samples of equal size. So, but just for the sake of simplicity, I just wanted to indicate that the top tells you the difference between the means. And the bottom is a measure of how much fuzz, how much overlap, how much how much variability there is in the groups. And so that's the basic model for most of this, for all of the statistical tests that I'm familiar with. So I've just gone through that. This was originally developed by someone by the name of William S. Gossett, who was working for the Guinness Brewing Company. And since all of his findings were owned by the company, he decided to publish his results under the pseudonym of student, which is why this is called the student t-test. Okay. Let's just look at the situation where we've got two groups where it's probably unlikely that, or almost impossible that there's any difference between the groups. Basically, I've tried to graph the two groups. Someone indicated to me that I don't have any labels on my axes. So basically, on the x-axis, we've got, let's say, our usual pain scale from 0 to 10. And on the y-axis, we have the number of people at each point along the pain scale. And so what you can kind of see is that the groups overlap. not only do they overlap, they're pretty much the same. So it's probably unlikely or highly, that we have any difference between the groups. And so just to give you some idea of what the numbers are here. The mean for the real and placebo group is 5.5. So right away you have the fact that the difference is 0. 5.5 minus 5.5 is 0. Standard deviation for both groups is 1.25 and is equal to 28 for both groups. If you want to have if you don't want to buy a statistical package, there are plenty of calculators available online, and one of them is given at the top. If you plug these numbers into this GraphPad calculator, you get the t-test is 0 and the probability, and well, just out of curiosity, what do you think the probability of the t-test is going to be? What's the probability that these two groups came from the same population? Lou? Yeah. And so, yeah, I mean, zero is a real number for a t-test. Usually doesn't happen, but it's a real number. It can happen. So if there's like 0 difference between the two samples, it kind of says that there's no difference between those groups, and you have to, as the saying goes, you have to accept the null hypothesis that they come from the same population. So basically, the p-value is 1, that they are from the same population. So that's your conclusion, that these two groups, there's no difference between them, so therefore the populations that they come from are not different from one another. So here's an example where we've upped the odds, and same things. I've graphed these two groups where we've got a pain scale, and what you can see is that there's more of a difference here between the two groups. And so it looks like the real group, the sample that got the real treatment, is doing much better because its mean pain is a lot lower than the pain for the placebo group. And so I would say that this shows that there's a real difference, that there's an effect for the treatment. So the mean for the real group is 3.5, the mean for the placebo group is 6.5, standard deviation is 1.25. If you crank this out in this GraphPad calculator online, the t-test value is 8.98, and the p-value of the test statistic is less than 0.001. I think gave up after about 5. They're like 0.00000, something like that. So basically, it's less than 0.001. So what would you conclude here? Are they from the same population or not? Okay. So basically, in this case, if we decided our level of significance is 0.05, then we would conclude that the p-value is less than 0.05, which is what we accept as our threshold for saying that something is that this p-value is too low to be considered evidence for the two samples coming from the same population, and so we have to conclude that they don't come from the same population. So in this case, we have a significant difference between the two groups at where significance equal to 0.05 and the p-value is less than 0.001. Okay. Third example, here we've got a t-test for two groups where there's a little bit more overlap. I mean, so it's kind of hard just by eyeballing it to say that there's any difference between these two groups. There's maybe some, but this is where statistics come in. This is where you need some way of evaluating whether or not the difference between the two groups is something meaningful or something that you actually think is real. So in this case, oh no, one at a time. Okay. Here, the mean for the real group is 5.5. The mean for the placebo group is 6.5. So you only have a one point difference. And standard deviation is 1.25 and is equal to 28. T-test is 2.99. P-value of the t-test is 0.004. So what do we conclude? Is there a significant difference between these two samples? Okay, so it's less than what we accept as our threshold for saying that something is significant. So we say that there's a significant difference between these two samples, and therefore they come from two different populations at this point. And so we then conclude that the treatment is effective. All right. Okay. Let's look at the formula again. And what happens to the t-test if the difference between the two means is larger? This is what we just saw with these three examples. What happens to, as we increase the t-test, as we increase the numerator, the difference between the two groups, what happens to the t-test? Anyone?
The statistic gets larger?
Yeah. So the t-test becomes larger. The larger the t-test, the smaller the p-value. Okay? What happens if the sample ends, the sample sizes are larger? So what happens if the n is something that goes in the denominator. So if the n gets larger, the denominator becomes smaller. And the smaller the denominator, what happens to the overall test statistic? Yeah. So we really don't have any control over things like standard deviations. We don't have control over what kind of means we're going to encounter in the real world. But we do have control over the n that we can get for our samples, especially if we're planning a clinical trial. So one of the key points about having the ability to say that there's a significant difference is to have as large a sample size as possible. And this goes into sample size estimation, power estimation, and this is actually a different topic. But I just want to kind of point out the fact that the sample size is very important, especially when you're planning a clinical trial. And so, yeah, Dr. Kaplan.
I'm kind of lost in terms of how do you relate the t-test to the p-value? It's not.
Okay. Yeah. So the question is, how do you relate the p-value to the t-test? And so the t-test is just a number that you get by putting in the means, standard deviations, and the n. But then there's a way of finding out what the probability of getting that t-test statistic is, based on the fact that you assume that there's no difference between the populations they come from. So those are two separate things. You calculate the statistic, and then you find out what the p-value is. Yeah. Okay. Usually that comes like, if you're using a statistical package, that's done automatically. So it calculates the t-value or the statistic value, and then it also gives you what the calculated p-value is for that statistic. Okay. All right. So far we've been talking about two separate groups. We very often, when we're doing clinical trials, especially in the early stages, we might use a before and after comparison. We have the same sample measured before and after some sort of treatment. And so this is known as having dependent samples or correlated samples, paired samples, or it's also known as repeated measures. This idea of repeated measures, we measure them once and then we measure them another time. Okay? Here's the formula for the dependent sample t-test. And it looks pretty much like what we had for the one for the independent groups, except there's a little bit of an added feature, which is if you look over here, there's this R here. That R is a correlation statistic. It's a measure of how much relationship, how much correlation there is between the two samples. And the nice thing about that is that it takes advantage of the fact that there's a correlation between your two samples. And so if there is a correlation between your two samples, your variability can be explained by that correlation. So the variability is no longer garbage or error or whatever. And basically you can just eliminate it from the equation. And so that's one of the advantages of using repeated measures or using correlated samples. You get a cleaner measure of the denominator is smaller. And what happens when the denominator becomes smaller in this kind of statistic?
The statistic gets larger.
Yeah. So the statistic gets larger. And so it's another way of trying to make sure that you have what's called more power, the ability to reject or the ability to say that there's a significant difference. Okay? So I think I just said that, right? All right. So let's take some sort of example of how you would use a dependent samples t-test. So let's say that we've got it's a very small clinical trial involving 4 diabetic patients measured for HbA1c. You can tell I've been working with endocrinology. So basically, they undergo some sort of some education program to modify their eating and exercise habits. And then what you'd expect is that A1C should decrease as a result of this intervention because they have a better lifestyle, they're eating better. So the pre-mean, so before the education, A1C is 8.78, and after the education program, it's 7.84. Standard deviation is 1.01. The post-standard deviation is 1.10. Correlation R between the two measures is 0.45, and your N is 4. So if you put all those in the formula, you'll crank out the following answer. T-test is 1.70, and the p-value is 0.19. So is there a significant difference between these two samples, or did it? All right. So you can conclude that basically these patients remained in the same, represent the same population that they came from. That the education program was not effective. Now, if we had a situation where the two sets of data were correlated not by 0.45 but 0.90, the correlation were higher, we redo the calculations. Our t-test is 3.92 and the p is 0.03. So the correlation is very important in determining whether or not you get a difference that's significant. Yeah, Ricardo.
Make the correlation higher. What would be an example?
Well, I could say, like better measurement. So measurement error is really crucial. So, for example, people copying down the wrong information for the patient, or lab results that are not reliable. So all those can be crucial for determining the correlation. You can also maybe use a better measure of insulin and levels. So like there are a couple of ways of increasing that correlation to try to maximize the correlation and minimize the denominator, so you're more likely to get a significant difference. Okay. Well, we talked about 2 groups so far. Independent groups, dependent groups. What about more complicated designs? Basically, a lot of clinical trials try to use, if not a real placebo, then very often there'll be like a placebo group, an active group, and then perhaps an active sham or an active placebo. So in this case, this is some work I've been doing with the Center for Health and Healing, which does complementary medicine. So we've got a trial for acupuncture for relieving pain in hip replacement surgery patients. So we have 3 groups. Group 1 gets real acupuncture. Group 2 gets a standard orientation about dealing with pain, some imagery, that kind of thing. Group 3 gets a sham acupuncture. So it could be it could be placing the needles in some different place, or it could just be, basically, you can understand the idea of sham here. So it's asking the question, is it important that the needles be placed in the accurate places according to acupuncture, or is it just being stuck by needles? Could it be just some sort of placebo effect? Okay. Now, we have a problem. Every time we do a statistical test, we'd like our significance level to be whatever we choose it to be. And let's say we choose it to be 0.05. We'd like it to be 0.05 for all of our comparisons. Now, the problem is that if we've got 3 groups, we've got 3 possible comparisons. And so we have group 1 versus 2, 1 versus 3, and 2 versus 3. We're doing 3 tests at the same time. And so we're kind of increasing our chances of finding a difference just by chance. It's a little bit like playing lotto. The more times you play, then the more likely you are to win something just by chance. It's not that you're finding anything real. It's just like you play it often enough, or you do enough statistical tests, you're going to find something just by chance. And so what we'd like to do is make sure that we have a level of significance that's 0.05 or constant for all comparisons. And so that's where the analysis of variance comes in. And basically, the analysis of variance compares the differences in means for more than two groups. And basically, it ensures that there's one single p-value for all the groups simultaneously that we can compare against one single level of significance. And basically, it kind of gives you some idea of whether there's any significant difference between any of the groups that you're comparing. So it could be between 1 and 2, 1 and 3, 1, 2 and 3, or it could be all three of them could be different from one another. And what we'll see is that, well, there's a problem with that, but we'll get to that. For the analysis of variance, the test statistic is the F-test. And here, basically, the denominator is kind of familiar. It measures the amount of variability within each group. So it's pretty much like the denominator of the t-test. The numerator measures how much variability or variance there is due to differences between the groups. So that's similar to what the t-test numerator is trying to tell you. But how does that work? How does variance tell you that? Basically, if you look here, the amount of variability that you have is a function of two things. One is the variability within each group. So like for the placebo group, its variability goes from here to here. The variability for the real group goes from here to here. The variability for the green group or the sham group goes from here to here. So partly the variability for everyone is due to the fact that people within each group vary. And that's kind of our usual error, our usual overlap. But there's some variability. If you look here, from here to here, some of this variability is due to the fact that the mean for this group and this group and this group differ from one another. And that's your variability between groups, or the variance between groups. And that's, so if you measure if you use variance as your measure of the differences between the groups, that gives you, and you compare that relative to the variability within each group, that gives you something similar to what the t-test does for two groups. Okay. There's another calculator for doing F-tests for single factor or simple analysis of variance. And but basically, if you crank all these numbers into that formula or into that calculator, your F is 17.70. Your P is less than 0.001. And I guess, what would you conclude here? Is there a difference? Is there a significant difference or not? Yes. Okay. So the opposite is in this case, where basically what you see is that the variability overall is from here to here, and it looks like there's nothing that's contributed to the variability. There's nothing contributing. There's nothing in terms of differences between the groups that are contributing to the variability overall. So in this case, the F, let's see if I can calculate it. Yeah. The F, all the variability is due to within group variability. So basically, the F is going to be 1.0. I'm sorry, the F is going to be 0. No, it's actually going to be 1.0. The p-value is going to be 1.0 also. And then the conclusion would be? Yeah. Okay. The F-test is called an omnibus test because it just tells you that there's some difference lurking somewhere if it's significant. And it could be one pair, it could be two pairs, it could be all three pairs if you're comparing three groups. So then you get into, well, how do you know which ones are different? Well, you could fall back and just do t-tests, but then you have the problem of the fact you've got multiple comparisons. And so to avoid that, way back when, they came up with kind of super t-tests that basically controlled for the number of comparisons you made. And basically, it meant that the overall level of significance was held constant for all of your comparisons. And there are some examples like the Newman coils and the Tukey HSD or Tukey honestly significance difference test. And they're not commonly used nowadays for a number of reasons. They tend to be very complicated, and also they can't be used in repeated measures analyses. And that's often what you encounter in medical research. And so if you can't use it with repeated measures, then there's a problem. Okay. Without getting into a lot of complicated stuff, probably the simplest post-hoc test to do is called a Bonferroni test. And the Bonferroni correction is very simple. Basically, if you have three comparisons, three statistical tests you're doing, and you want to control for the overall alpha and have that at 0.05, basically what you do is you take your usual alpha and you divide that by 3, which means that and that gives you a new alpha of 0.0167. That's what you apply to each of your statistical tests. And so it means that, for example, in the first example with the analysis of variance, the real versus sham, that p-value was 0.03. The real versus placebo was less than 0.001, and the sham versus placebo was less than 0.001. Now, if you apply this corrected alpha, the Bonferroni corrected alpha of 0.0167 to each of these comparisons, then it turns out the real versus sham is not significantly different. Right? Whereas both of them are different from placebo. And, if kind of simplistically what you'd then conclude is that there really isn't any difference between the real and the sham, and then maybe, you conclude that really there's no difference between putting the needles in the correct place versus just sticking people. So actually there are a couple of things you could do to, there are a couple of variations on the Bonferroni correction that you can do, and actually at least one of those will give you a difference for the real versus sham, but basically that's what you need a statistician for. Yeah, Lara.
How would you weigh the decision to use the Bonferroni correction versus the 2 PhD, or should you talk to your biostatistician?
You should always talk to your biostatistician, but aside from that, the fact is that you could use, since these are 3 separate groups, you could use one of the post-hoc tests. Either one. Actually, it's kind of a toss-up. A lot of times you'll get the same result. So actually, you could do it both ways, or you'd have to kind of decide whether or not. Sometimes those post-hoc tests are a little bit stronger than a Bonferroni, in which case maybe you'd use that. Okay, but most of the time I don't wind up using a post-hoc simply because I'm usually using repeated measures analyses. Okay. Multi-way ANOVA. And let's see. In this case, I think I was working with both the Center for Complementary Medicine and with endocrinology. No, actually, this was with renal, with the dialysis department. Basically, it's looking at 3 different treatments. So we have 3 treatments for trying to improve glomerular flow rate in patients with renal problems. And so one of them was fish oil, one of them was extra virgin olive oil, and one of them was mineral oil. But one of the things they were interested in looking at was whether or not there were differences between males and females in terms of the way they responded to the treatment. And so does the effect of the treatment depend on gender? And so the whole idea here is you want to see whether there's an interaction between the treatment and gender. And so it's the idea, does the treatment make a difference depending on which group you make? And so that's a very important consideration in a lot of medical designs, whether or not there are specific patient differences in the way they respond to treatment. So that's why you'll often find that they'll do sub-analyses to see whether or not there are specific groups that respond better to the treatment than others. Here's the overall comparison for the treatments. What you can see is that basically mineral oil and olive oil seem to be kind of similar. Fish oil seems to be doing a lot better. Well, I wouldn't conclude anything just now because what I would want to do is look at the interaction. Here's the overall comparison of gender. It looks like the females are doing better. But let's look at what happens if we look at the combined treatment by gender graph. So in this case, what you can see is like in general, females do better And it looks as if the difference is constant. So even though females do better, it's not that there's any interaction between gender and the treatment. It looks like in general females do better, and so depending on what you give, the females will do better. But it does indicate that fish oil in general is better than the other two treatments. Okay. Here's another possibility. Here's where there's some evidence of interaction. And I'm not giving any p-values or anything like this. This is just to demonstrate the fact that there's another possibility that you'll find is that the treatment does do much better for one group versus another. And so that's indicated by the fact that the graph goes, the line for the females goes up much higher. The elevation goes up much more for the fish oil than for the other two. So it looks like, if you just took these two groups, there's no interaction for these two treatments. But it looks like females are responding much better to the treatment. And that's something that you'd be very interested in knowing in tailoring treatment for your patients. Okay? So that's one of the importance of looking at and using multi-way analyses of variance. Looking at not just simple differences between the treatments, but also whether there are differences based on other group factors. Okay. Repeated measures. I'm going to try to go through this quickly because we're getting close to 9 o'clock. We're, again, looking at the effect of the education program on hemoglobin A1C. Here we're looking at 3 points in time, before, after, and then 6 months after the education program. With education programs, it's easy to find a difference before and after. It's like if you get them right after the end of the education program, they're really hepped up. They're familiar with everything, and it's like you'll really get differences. But it's like whether there's a long-term difference that's really much more important. And usually 6 months is considered a kind of benchmark for showing that like education programs or treatments really do some sort of a long-term good. And so here, what we see is that with this group, okay, here. Okay. So here, hemoglobin A1C at before, it goes down after. Here, it's back up after 6 months, which kind of says they've been backsliding. They haven't been keeping up with whatever they were learning. And so basically, it says there's no long-term follow-up or no long-term benefit for this program. Whereas, if we look here, if we saw this kind of pattern, this would be evidence for some sort of long-term maintenance of whatever they had learned in the training program. So this is the kind of thing you'd like to see in an education program. All right? So then let's do the same thing we did before. Let's look at a multi-factor analysis. Let's see whether gender makes a difference. And so here would be one example where there's long-term maintenance, and it doesn't seem to be very much different for, in this case, we're looking at older versus younger patients. All right, so it says this program will work for both younger and older patients. Okay? If we look here, it kind of looks like, the older patients aren't benefited as much. They're backsliding. The younger ones seem to be a little bit more receptive to the training, and they're the ones who are actually improving over time. Okay? So these are the kinds of things that a multi-way analysis of variance, whether it's separate groups or repeated measures, will tell you. And that's the value of looking at interaction effects. It tells you what are the differences, what sort of differences there are between groups for their receptivity to treatment. Okay. Repeated measures ANOVA, problems with it. Traditionally, if you have repeated measures analysis of variance, if you have missing data, then the patient has to be dropped from the analysis. And if you have fewer patients in the analysis, that means that your power goes down. It means your ability to say that there's a significant difference between the groups or among the groups is decreased. So that's very much a problem. That's why patients who drop out from a clinical trial are always a problem. And without getting into a lot of other issues, I'm going to talk about basically the traditional analysis of variance has that problem with missing data. It also has problems with normality. Normality, t-tests and f-tests are considered parametric tests. They assume normality in terms of their calculation, in terms of how you calculate the p-value. And so they're called parametric tests because they depend on the parameters of the mean, which are, they depend on the parameters of the normal distribution, which are the mean and standard deviation. And way back when, people came up with things that called non-parametric tests, which didn't depend on normality, and they were developed for data that were not normal, so the things that were the data that had outliers. So it's a little bit simplistic to say, but typically non-parametric tests are often less powerful than parametric tests. But the other problem with them is that you can't do very much with them except for like group comparisons. So you can't do anything more complicated. You can't do multi-way comparisons, and so they're kind of limited. Yeah?
Would it be helpful to just point out that the reason a non-parametric test is less powerful is because a parametric test assumes something about the structure of the data.
Yeah.
And once you make that assumption, what you get is increased likelihood of finding differences, but that's based on your
assumptions.
Making an assumption about the population, which may or may not be true.
Yeah, in general, in terms of like power, the more information you have, or you can assume, the more power you have, and the more likely you are to get a significant difference. So that's kind of, when you have a larger sample, you have more information. When you can assume normality, you have more information. So that's kind of a general rule.
Well, yeah, but it's made up information. In other words, it's a trade-off that says, if you allow me to assume this, then I can make a more precise comparison. If the assumption is wrong, you've made a more precise
error,
but more false assumption.
Okay. All right. I'm just going to touch on them, and these are kind of very super treatments of both of these. Kind of the answer to the two problems I just mentioned. The problem with missing data, actually, it can be solved in a number of ways. There are things called multiple imputation, where you basically use ways for figuring out ways of filling in the missing data. But something called mixed model regression, actually also generalized linear modeling, make different assumptions about the correlations that come from the data. And so they can actually be used in instances where you have missing data, and they'll simply take into account the amount of the people that you do have and try to come up with the best possible correlation based on the data you have. So someone who's missing some data can still be included in the analysis. The other nice thing about generalized linear modeling is that it can be used with non-normal data. So it can be used with, and can be used to look at non-normal data over time. So things that are yes-no kinds of things like you'd use with a chi-square, but looking at it over time. And also, it can be used with skewed data. So these are kind of the trends of the future, and this is what you'll see more and more in the literature. And so basically, there are things that are based on what have been traditional in terms of like analysis of variance, but they've gone on and plugged some of the problems that have held with traditional methods like analysis of variance and t-tests. And that's basically all I have for my talk. I'm open to questions.